In this video, I will walk you through several problems from my Unit 7 AP Calculus test. In Unit 7, we explore the applications of 7 calculus theorems. The first fundamental theorem of calculus, the second fundamental theorem of calculus, and 5 existence theorems, which we will talk about later. These problems will be considered calculator active, so we will use our graphing calculator as needed. For problem number 1, they are asking us to find the equation of a tangent line. Whenever they ask us to do that, we always use point-slope form, which reminds us that all we need is a point and the slope. We are told that the line is tangent to the graph of g at x equals 5. So, the x value of the point is 5. In order to find the y value, all we have to do is evaluate g at 5. Evaluating g at 5 means plugging 5 in for x. If we put 5 right here, that's 5 squared, which is 25. We can evaluate this integral on the calculator. So we want to integrate from 1 to 25. So hit Math 9, and we're going to go from 1 to 25. So I know we need a fraction in here. So let's do alpha y equals enter. And it was 1 over something. What was it? 1 over 3 plus cosine t. 3 plus cosine. Instead of t, we have to put x. And dx. So there it is. 8.592 if you round up, or 8.591 if you truncate. With this y-coordinate, we now have the point that we need to write the equation of the tangent line. All we need now is the slope. So we need to find g prime at 5, because that will give us the slope. But first we need an expression for g prime of x. But how do you take the derivative of an integral defined function? The second fundamental theorem of calculus tells us how to take the derivative of an integral defined function. We have two different versions. There's the common case, which we get to use when we have a lower limit of integration that is just a constant, and the upper limit is just x. In that case, g prime is simply f of x, the function inside. That's not the situation in which we find ourselves right now. We are in the general case. For the general case, where you have something more than just a constant and x, to take the derivative, we have to take the upper limit and plug it in to the function that we have, and then immediately multiply by the derivative of the upper limit. And then you subtract, and you plug in the lower limit times the derivative of the lower limit. So again, the derivative in general for an integral defined function goes plug in the top times the derivative of the top minus plug in the bottom times the derivative of the bottom. So that is what we are about to do. First, we plug in the upper limit. So if I take this x squared and I plug it in right there, that's going to give me 1 over 3 plus cosine x squared. You plug in the top times the derivative of the top. So the derivative of x squared is 2x. So we have to multiply it by 2x, which I am going to put in the top. All right, so we plugged in the top times the derivative of the top, minus. Now we're going to plug in the bottom times the derivative of the bottom. But that would be 1 over 3 plus cosine 1. So there I plugged in the bottom. However, the derivative of the lower limit is 0. The derivative of any constant is going to be 0. And when I multiply by 0, that's going to wipe this whole thing out. So I'm not actually going to write this at all. So this is g prime of x. This will give me the slope at any value of x that I choose. I want the slope at x equals 5, so I'm going to evaluate g prime at 5. So that will be 2 times 5 over 3 plus the cosine of 5 squared. I can just go ahead and put 25. So I can just put this in my calculator. I'll probably type it in as 10 over 3 plus cosine 25. So here it is, and kabam, 2.506 if you round up. Now we are ready to write the equation of the tangent line. It goes y minus y, so y minus 8.592 is equal to the slope, which is 2.506, times x minus x, so x minus 5. So that's it for problem number 1. At a gravel processing plant, there are 4 tons of gravel in a pile at time t equals 0. Gravel is added to the pile at a rate given by E of t equals 1 plus sine of cosine t for values of t between 0 and 5, where E is measured in tons per hour and t is measured in hours. As long as there is gravel in the pile, gravel is removed from the pile and placed on a conveyor belt at a constant rate of 1.5 tons per hour. Number 2. How much gravel is added to the pile during the interval from t equals 0 hours to t equals 3 hours? A fundamental concept in calculus is that the integral of a rate will give you the change in amount. So here they are asking us for the amount of gravel that is added to the pile. So they're asking us for the change in the amount of gravel. So we need to find the integral of the rate at which gravel is being added to the pile. All right, the integral of a rate is the change in amount. But the function that gives the rate at which gravel is added to the pile is function e. So we need the integral of e of t dt. This will give us the change in the amount of gravel. If I want the change between t equals 0 and t equals 3, then I need to apply those particular limits of integration. This is what I call a rate in, rate out problem, because they gave us a function for the rate at which gravel is added and the rate at which gravel is removed. Let's put both of these functions in our calculator as y1 and y2, like this. I can now evaluate this integral, and if I need to deal with function e later, I won't have to type it in again. For the integral, we do math 9. We want to integrate from 0 to 3. We typed e of t into y1. We can access this by typing vars, switching over to y vars, hitting enter, and choosing y1. And dx. That's it, 3.119. So that's it for problem number 2. Number 3, at time t equals 3 hours, is the pile of gravel getting bigger or smaller? Explain your reasoning. On a rate in, rate out problem, if you want to know if the amount is increasing or decreasing, compare the rate in with the rate out. Remember that the rate in is given by E of t. So in this case, we want to know what is the rate in at 3. So we need to evaluate E of 3. We can do this using our calculator. Hit the window button, well, actually second window, and make sure that you switch from auto to ask on this setting right here. Once that is done, you can hit second graph to access the table menu. If I put a value right here for x, the calculator will evaluate any functions that we have in y1, or y2. So I'm typing in a 3. So this is the value of y1 at 3, and this is the value of y2. Of course, y2 is a constant, so that's not going to change. But this is the value of e at 3, because we typed in e as y1. So the rate in at t equals 3 is 0.164 tons per hour. In other words, 0.16 tons per hour are being added to the pile at t equals 3 hours. Notice that the rate out is a constant 1.5 tons per hour. Since the rate in is less than the rate out, then the amount of gravel in the pile is getting smaller. In other words, the pile of gravel is getting smaller at t equals 3 hours because e at 3 is less than 1.5 tons per hour. Notice that it's not enough to simply say that the rate in is less than the rate out. You must say that e at 3 is less than 1.5 tons per hour. Number 4. At time t equals 5 hours, gravel stops being added to the pile, but continues to be removed at the same rate as before. At what time t greater than 5 will the pile become empty? We are about to use the first fundamental theorem of calculus. However, we already said that the integral of a rate gives you the change in the amount. Once you have memorized that, this theorem is really just common sense. The end amount is going to equal some initial amount plus the change in amount, of course. For a rate in, rate out problem, this becomes the end amount is equal to the initial amount plus the amount added minus the amount removed. We are setting up an equation that will tell us when the pile will become empty, so the end amount will be 0. In the setup, we are told that there are 4 tons of gravel in the pile at time t equals 0. So the initial amount is 4 tons at time t equals 0. Next, we need an expression for the amount of gravel added to the pile. We know that the integral of a rate is the change in amount. So the integral of the rate in should give us the amount added. We are talking about a time from 0 to 5 because we are told that at t equals 5 hours, gravel stops being added. So that's why we have this upper limit of integration. So this is the expression for the total amount of gravel added during the entire time. Finally, we need an expression for the amount of gravel removed. So this integral will be open-ended. We're still starting at time t equals 0. But gravel continues to be removed after t equals 5 hours at the same rate as always of 1.5 tons per hour. But we are trying to find the time t when the pile goes empty. So we don't know how long this interval will be, so we put a t to represent the unknown time. And we'll finish it off, but we can't put a dt when you have an integral defined function like this with a variable. You can't use the same variable as the limit and inside the function. So you really can use any variable here. I'm going to use an x, but just make it something other than t. Here's a quick side lesson on how to take the definite integral of a constant. First of all, here is a shortcut. The difference in the limits of integration, 7 minus 3, in this case is 4. So you're going to wind up just multiplying 4 times 5. So, whoops, why did I put 0? So this is going to end up being 20. Here's how that would look if we did it the long way. The antiderivative of 5 would be 5x. But then we apply the limits of integration from 3 to 7. That means we're going to put in 7 times 5 minus 5 times 3. Well, that's going to be 35 minus 15. But guess what? That's 20. So the shortcut is much faster. Let's do another one for practice. What would be the definite integral of 4 in this case? Well, 8 minus 2 is 6. So ultimately it will just be 6 times 4, which is 24. Almost done. How about now? Well, 8 minus 0 is just 8. So in this case, we will end up with 8 times 4, which is 32. What if we have a variable instead of this 8? What if we have a t right here? Well, t minus 0 is t, and then t times 4 is 4t. I recopied the first few terms, and now I am up to here. Using the shortcut I taught you in the side lesson, the integral of 1.5 from 0 to t will be 1.5 t. We could have come up with this by common sense, because we know that gravel is being removed at a constant rate of 1.5 tons per hour. So, of course, the amount of gravel removed will be 1.5 times the number of hours, or 1.5 t. So if you understood what I just said, then you will immediately just write minus 1.5 t. Otherwise, you will go through the motions, set up this integral, and then use the shortcut to turn this into minus 1.5 t. Finally, we need to solve this for t to find how many hours it will take for the pile to be empty. Let us add 1.5 t to both sides of the equation. So now we have this. Finally, we need to divide both sides by 1.5. That will give us the value of t. So we can type all of this into the calculator. Let's start by creating a fraction. Alpha y equals enter. In the top, we have 4 plus. For the integral, we do math 9. We are integrating from 0 to 5, and we are integrating e of t, which we stored in y1. So we will hit vars, y vars, enter, enter. So that's the numerator. But then we are dividing by 1.5. And that's it. 5.432 if you round up. So that's it for number 4.